Great. Thank you, Tommy, for this very special Distinguished Colloquium of Robotics. It's a pleasure for me to introduce Professor Don Tilbury from University of Michigan. I have the pleasure of knowing Don for, I think, about 33 years. We were both at graduate students. And
we were only 4 years old at the time.
So this was a time in the late 90s. There was no World Wide Web. There was the internet for email. There was no social media. There was no smartphones, and we survived. We worked from 8 a.m. till 10 p.m. at night. So Dawn, we had a pleasure of knowing, and she's as thorough as wonderful researcher. I was just telling her she hasn't changed. Very meticulous, as she always was. She did a great dissertation on applying, control theory ideas to non-harmonic. Her dissertation work is still well cited. After finishing from Berkeley, where she also got an award for her best dissertation ECS. She was a faculty at Michigan since 1995. Doing a lot of amazing work in control, robotics, and other areas. I think if I start talking about her work, that'll take an whole hour. So, you can go check out her profile on Google Scholar or something else. But Dawn also has been very influential in a lot of other roles. She was the Assistant Director of Engineering Directorate. If you ever got funded by NSF in the last few years, probably Dawn wrote the check indirectly, right? So, and she's only managing $1 billion plus. No, not too much, that was it. And she also told me that when she was at NSF, she also did some big initiative with our President Pine. So she already has great ties to UMD. And so huge influential thing at NSF, she made a huge impact in engineering, computer science, and all across. A lot of things she did impact the whole nation, all the education and all the engineering program. And now she's doing another exciting role. Michigan, which is one of the best college of engineering, have a new department of robotics. A department of computer science, department of EC, mechanical, aeronautical engineering. Of course, we are MRC and we are robotics minor, but Michigan did a bold thing. They have a department of robotics. So you can be undergraduate major in robotics, and she's the inaugural chair. So she's doing the research, the education, the budget fights, and the administration. And I think this is a trend we're going to follow nationwide. So she told me we can get us for another talk sometime on how to be a dealing with robotics department. But we are so glad that she's able to find time and visit us at Maryland today. And a talk, you can see title about human interaction, autonomous vehicles, and trust. I would say this talk has at least 3 components. There's autonomous vehicles, which is still one of the hottest challenging problem in AI, human-robot interaction, okay? But she brings a whole component of trust. How do autonomy and human interact? So we'll see all 3 dimensions. Welcome, Dawn, and we have a pleasure to have you here.
Well, thank you, Dinesh. And I was just telling Dinesh it's great to be back giving a seminar in person and see some smiling faces out there. The last several seminars I've given have all been over Zoom, which is, great to reach people all over the world, and also unsatisfactory to not see the in-person connection and questions. So I'm happy to be here at the University of Maryland. It's been a while since I've been here, but it's always been a great place. So I'll tell you about some of the work that we've done in this idea of humans interacting with automated vehicles and how to calibrate trust. And this work has been mostly done by graduate students, as most research is, and in collaboration with a colleague of mine who's actually in the School of Information and trained as a social psychologist who studies trust. So I bring a control perspective. He brings a psychology perspective and human behavior, and we did some work on how to model and calibrate trust. So Dinesh mentioned our new robotics department. What you see on the screen is the building we have for our department. It's quite beautiful. The weather's beautiful like that in Michigan all year round, as you might imagine. And no, it's a great building for collaboration. So, but we'll go on ahead with the outline. So this is very briefly, I'll talk about trust and trust in automated vehicles. What does that mean? How do we model it? How do we estimate it? And how do we calibrate it? And then I'll talk a little bit about pedestrians trusting in automated vehicles. And I will say, having walked around campus a little bit this morning, there's a lot of interesting trust questions when you're trying to cross in front of buses and cars here on campus, just like we have in Ann Arbor. And then I'll wrap up at the end with some conclusions and think about the future directions. And I'd be happy to take questions at the end. This is a topic that I think generates a lot of discussion. So we all know from experience how trust is an important variable for human interaction, humans to humans. And as we start to build robotics that interact with humans, research has shown that trust between a human and a robot, how much does the human trust the robot, can be really important to get the activities that the robot can help the human with. If the human doesn't trust the robot, they're not going to use it. And so how can we facilitate that trust? And so people will consider that trust when they're making decisions about interacting with robots, as with other forms of autonomy. So we'd like to get to the point where robots are not just a tool that people can use, but a teammate. Then humans and robots can work together as a team to accomplish goals that either of them would have difficulty achieving by themselves or working independently. So we define trust, and this is, again, coming from the social science literature, as the attitude that an agent will help achieve an individual's goal in a situation characterized by uncertainty and vulnerability. There has to be some level of vulnerability in order for trust to really be effective. You might think about the agent that suggests what movie you should watch next. Maybe there's a little bit of vulnerability there. If you don't like the movie, you're going to waste some time. But it's not like driving an automated vehicle where if the AV screws up, you might get in a crash and hurt yourself or someone else. So definitely vulnerability as well as uncertainty. So there has been a lot of research done over many years in terms of what affects people's trust. What are the conditions that are important for people to trust, and how does trust evolve over time? We're also going to, because we're going to try to estimate and model trust, we're going to try to understand what behaviors do people who trust exhibit, because we can observe their behavior. And so we're going to focus on human-robot interaction, where humans and robots are cooperating to achieve a goal. And in particular, in this talk, a robot's going to be an automated vehicle. So automated vehicles are robots. They interact with the world. They sense their environment. They make decisions. They take actions. And safety and comfort are certainly important for people who are riding in automated vehicles. And so all the research you've seen and the hype you've heard about with Tesla and GM and their Super Cruise and all these companies that are trying to put up self-driving cars, theory is that it's going to improve transportation. But that's going to depend on people trusting them. So how many people have ridden in an AV? No? A handful. So I think you'll see this more and more. You can come to Ann Arbor. We have a free service from a self-driving car that will take you around town. It doesn't go very far. Like, I could walk that far. But, it's kind of fun to say you're riding in an automated vehicle just to try it out. But they're a little bit quirky. They don't necessarily behave like you would expect a human driver to behave. So when we talk about trust, we want the humans to trust the AV appropriately. And there's two major sides of trust miscalibration or inappropriate trust. There can be undertrust, where the person doesn't trust the automation or the robot. And here we say this is disusing the automation or disusing the autonomy. The person here might be driving an automated vehicle, but he's looking straight ahead at the road and got his hands gripped to the wheel. He's not using the automation of the vehicle, taking advantage of that to do something else that he could be doing. Taking a nap, doing a crossword puzzle, watching a movie, reading email. Not that I recommend doing those things if you're driving an automated vehicle. But, he's not trusting this vehicle. There's also overtrust. And you've seen the stories in the news where someone trusts that their Tesla is going to drive exactly like it's supposed to, and it doesn't. It runs into a guardrail, a pedestrian, another car. Accidents can happen. And that's because the driver trusted that vehicle too much beyond its level of capabilities. And so we don't want that to happen either. So we want to try to have the appropriate level of trust for the ability of the automation. We want the driver to trust the automation enough at a calibrated level in real time so they can take advantage of the automation to do some secondary task, and I'll tell you what we ask them to do, but not too much that they get into trouble and crash the AV. So I said we're going to try to model this level of trust in a human in a very specific scenario when they're driving a semi-automated vehicle. These vehicles that we have them, quote, drive, this is simulation video game style, is not totally autonomous, but it's what we would say is SAE levels 3 automated driving. So they're in this simulated driving environment in our lab. They can see the screen in front of them. And the automated driving system can do lane keeping. It can keep their speed, like cruise control. It has a forward collision alert if there's something in the lane ahead of it that needs to stop and get around. And it has emergency braking. So if the person listens to the alert and drives around the vehicle, then it, everything works fine. But the vehicle cannot change lanes autonomously. Now, some systems out there today can change lanes autonomously. We do not put that in our simulated system. We tell them they need to be able to take control of the car and drive around the obstacle when it appears in front of them in the screen. So this forward collision alert is imperfect. It can make mistakes. It can miss obstacles. But we don't crash the vehicle, even in simulation. We make sure that the emergency braking works perfectly. So on the bottom right, you can see there's a heads-up display, and it tells the driver if they're in the auto mode. You can see that little green thing in the middle. It says the vehicle's driving autonomously, and they can take over control at any time they want. So this is how the forward collision alert system works in our little simulated experiment. We track time as discrete events on every potential event in the system. Now, if there is an obstacle, then there's a true alarm. The collision alert sounds and says, stop the vehicle ahead, you need to take control now. And then they can come over, take control, drive around it, and put the autonomy back in. We also have false alarms where it says, stop the vehicle ahead, take over control. And if you look ahead, there's nothing. It's a clear road all ahead. It's just a false alarm. Happens. Maybe it was a shadow. Maybe there was a deer ran across. We don't do any of that in the simulation. It's just a false alarm. And then there's missed alarms. There is an obstacle ahead. It doesn't tell you. So if you don't notice it and take over, then the emergency brake will kick in and stop you. So we increment this discrete time per event. You can see K plus 1 is every event. In the simulation, there's about a minute or so between events. So this is not second by second. And so we use this notation. You'll see in our model, L is a true alarm, F is a false alarm, and M is a miss. So in the experimental setup, as I mentioned, the drivers can activate or deactivate the autonomous driving at any time. And we ask them, while they're sitting behind the wheel, letting this car drive them down this road, to do this non-driving related task. NDRT is what it's called in the literature, and this is a search. You can see there's a little iPad next to the driver's seat that has a screen like this with a bunch of O's and a single Q. Can you find the Q? It's kind of a tricky one, right? You have to kind of look at it, and they have to find the Q, and they get a point for every Q that they find. And as soon as they find the Q, then another screen comes up with lots of O's and a single Q. And so it's a search task, right? They have to pay attention, try to find that Q, and also look up and see if there's something happening on the road ahead. Now we ask them, after every event, did their trust in the automation change? Did their trust increase, which it might have if there was a true alarm. It gave me an alert. It told me there was an obstacle. I trust it more. Or maybe there was a missed alarm or a false alarm. And research shows, yes, trust decreases when the automation makes a mistake. But we measure that. The gold standard for measuring trust is by survey. So this is the gold standard of how much people trust the system. And we do this survey after every event, like I said, to self-report. Now we give them... What? Yes. We'll talk a little bit about that later. So I said they get 1 point for every cue they find, and if they miss the obstacle up ahead, either they don't pay attention to the alert, or it was a missed alert and they didn't notice, and the emergency braking kicks in, they lose 25 points. So that's kind of a lot of points. So we give them an extra bonus for more points they get. But of course, they get more points by finding the cues, not paying attention to the road. They lose points if they miss the obstacle. So we're trying to incentivize them to pay enough attention to both sides. So how do we model this trust? As was mentioned, self-reporting of trust is absolutely biased. People bias on how much they say they trust a system. So we'd like to be able to estimate in an aggregate how much people are trusting. So we come from a controls background, so we're going to build a model and estimate the driver's trust in the automation. Also, if this was really going to roll out in a real vehicle, you wouldn't want to stop your car every 5 or 10 minutes and fill out a survey on how much you trusted it. You'd want it to be able to estimate how much you were trusting the vehicle. There are existing models that use physiological sensors to measure people's trust, but mostly those either give you it's trusting or not trusting. And we'd like to have a calibrated trust, more trust or less trust, on a scale of, say, 1 to 10 or 0 to 100 or something. And then model how that trust dynamically changes over time as the vehicle makes mistakes and does the correct thing. And how does the human behave? How do their behaviors indicate that they're trusting the system? So many of you, I'm sure, know a lot about control, and so you can imagine to build a model, you need inputs and outputs and variables, and so here's our control systems model of trust. We have inputs to the system, which are the actions of the automated vehicle. Is there a true alarm, a false alarm, or a miss? And these are Boolean variables that we model. And we assume the automation knows if it was right or wrong. Maybe an over-assumption, but reasonable in our simulation. And then the outputs that we measure are the observed trusting behaviors. And these have all been shown in the literature to be correlated with trust. The focus. How much time does the driver look at the screen for the driving versus the screen for the search task, the non-driving related task? The usage of the automated driving. How much of the time do they use the automation versus take over? And finally, how well are they doing on the automated search task? Now, this is maybe a little bit of a cheat because in real life, if the person was reading their email, you wouldn't know what their performance was on their email. But in our little simulated system, this is absolutely correlated with their trust. Also correlated with their focus, right? How much of the time are they spending? That tells you how much time, how many points they're really getting. So we have the linear systems model, state space. The trust is a single variable, T. And it depends on the previous value of trust, as well as the inputs, these alarms, misses, and false alarms, and some noise. And then we observe the driver's behavior, which is also a function, linear function of trust. So we've got 3 inputs and 3 outputs and 1 state variable. So it's not maybe a very complicated linear model, but we can build this linear systems model with the observed behaviors that we see people going through the system, and then we can use that to build this model, and then we'll use that model for control. So as I mentioned, we ask, after each event, we ask about their trust change, and then at the end, we do a long survey to get their overall trust in the system. So in this experiment we ran, we had 4 types of system reliability. In one condition, everything was totally reliable, and in the other conditions, there were false alarms, or misses, or both. And that led us to fit these A, B, and C matrices, basically, to the data that we observed. So here you see the, so we have the automated driving system gives the inputs, true alarms, false alarms, and misses. That goes to the driver, who gives these observed variables. How much time do they focus on the driving versus the the search task and what's the performance on the search task, and the usage of the automated driving system. And we put those into our model, our estimator model, and we basically build a Kalman filter using that state space model, and then use that to estimate their trust over time. So this is the data that we did for training. So we take, I have to remember how many, 40 or so subjects through this experiment, and the let's make sure I get the right numbers. So the real observation in red is taken from the driver's self-reports, and the black line is the best estimate from the Kalman filter. And we assume, because we don't know anything else, that their trust is constant over each interval between two events. So each of these numbers on the bottom are the times of the different events. And the circles are true alarms, diamonds are false alarms, and triangles are misses. So you can see, what? Yeah, there is a, you'll see in the later plots, I'll show you the estimates of the variance. This is just the best estimate here. So you can see the trust goes up and down, but this driver was overall pretty trusting of the vehicle. You know, went up a little bit when there was a true alarm, the thing was behaving correctly, and then went down for some. This one, you can see the red line is the driver's self-report of trust. And the black line is our best estimate of their trust based on their behaviors. And so, again, we built the model not for each individual person. We could think about doing that. I don't think we have enough data right now. But we built that model, that Kalman filter model, based on the aggregate of everyone. So maybe this person underestimates how much they're actually trusting the vehicle, but their behavior basically shows they're trusting it a lot more than they report. And so this is an issue when you're dealing with these type of human subjects, because every human is a little bit different. But anyways, we use this state space model as our best estimate for the real-time driver's trust, based on observing their behaviors in the system. Well, okay, that's straight. That's just a model. But we wanted to try to calibrate their trust. And if they're over-trusting it or under-trusting it, can we get them to be more in alignment with the vehicle's capabilities? So we call this management. You know, we had a lot of discussions. Is this control? Well, kind of, but it's not like we're trying to track a set point. So we call management as estimating and calibrating, and try to identify significant or over or under trust to try to influence the drivers to correct their trust level. If they're under trusting, make them trust more. If they're over trusting, warn them and make them trust less. How can we do that? Well, again, these are conceptual ideas, but we do know that we can estimate their trust state, and then we can think about different capabilities of an automated vehicle. And we are going to use different road conditions. I'll talk a little bit about that on the next slide. And then the way we influence their trust is through communication. We warn them or we discourage them and say, hey, you need to pay more attention to the road. So this is the overall framework that we use for what we call trust management. You saw the trust estimator previously, takes the previous value of trust, and what happens from the automated vehicle to estimate the next trust. And then we look at, from the automated vehicle, what's the capability? Under what condition is the automated vehicle working? And then use that as feedback to send drive messages to the drivers. So we're still observing the same variables. They're focus on the driving task, focus on the search task, and use of the automation. Now, in this experiment, when we're trying to calibrate their trust, we set the system so that it was always correct. There were no misses, no false alarms. It always gave the driver a correct warning of a vehicle that was coming up ahead. However, the distance at which it could detect those obstacles was different for the different situations. If it was an easy road, like sunny day, highway, it could see those vehicles far away. If it's a mountain road with curves and hills, the distance at which it could detect those obstacles was much shorter. But like I said, all the alerts were correct in this calibration framework. So I mentioned we calibrate the truss by warning or, and here's the different capabilities. So there are 3 different types of roads, and every person drives all 3. The type A, this dark blue straight line, is high capability. Clear, highway, wide. And then there's a curvy portion, but still flat. That's medium capability. And then there's the red dirt road, which is low capability, kind of a bumpy road, a little bit hilly. And so the distance that where it can warn for the obstacle and give the emergency brake is different for these 3 different capabilities. And each driver goes through this twice, and once with the calibration and once without the calibration. And we flipped or randomly did those 2 in the opposite directions. And we had the same incentive system as we did in the first. They're doing the searches for the cues. They get points to find the cues. If the emergency brakes kicks in, they lose points because they haven't been paying enough attention. And the total compensation, this took, less than an hour. And so the minimum compensation was $15 and the maximum was $50, which is incentive for undergrads. Yes, question. The simulation. So if the automation is kicked in, then it will control a constant speed and stay in the lane. And if the subject takes over, they can change the speed and change lanes. So, except if it's coming up on an obstacle, then it will emergency brake. So that's in the automation. So this is our calibrator. You want to call this our control law. On the there's 4 different or matches that we can see. On the diagonal line, those tan are calibrated truss. The driver, the capability is low and the driver doesn't have a lot of trust, or the capability is high and the driver has high trust. So we call those calibrated, and we had 3 different capabilities, low, medium, high, and we more or less picked the low, medium, high trust. Again, lots of decisions went into this, but this seemed to work. So in the lower corner, in the blue, you can see if the system is under-trusting, it will encourage the driver to pay more attention to the search task. If the driver is over-trusting in the brown or the red, it will warn the driver to pay more attention to the road. And I have some videos. I think they'll work. We'll see. So. Can you guys hear that okay? So that was calibrated trust. It just says stop vehicle ahead. He's finding the cues.
Hey, this is an easy road. You don't need to worry about driving. I will take care of it while you focus on finding the cues.
So that was under-trusting, encouraging.
Hey, this part of the road is not very easy. You can still find the cues. But please pay more attention to the road.
This is the dirt road.
Look, I told you, I do need your attention.
Can I ask you a question?
The road is terrible. I don't know if I can keep us totally safe.
Can I ask you a question?
Yes, please. That's
So,
that.
I do the following experiments in my car.
Yeah.
The wiggle. And I get the text to tell me, do you want to go rest or something? Right? So which is an example of this kind of problem. So the question is, if you're going to give voice feedback, why do you need the points?
Well, so the reason to have the points is to, if the goal was to never crash the car, they would just watch the road the whole time. Right? Then there's no reason to find the cues. We want them to shift their attention appropriately to the capability of the,
Over here. And
in 5 seconds, well, that's why you trust the automation. We're finding how much they trust the automation. So anyways, I have these other slides are in case the video doesn't work. So this is the output of the warning messages. You can see the undertrusting on the vertical axis is delta t. How much did the driver's trust change? And this is not self-reported trust. This is our estimate of their trust based on their behavior, right? So if their trust increases, that means they're looking at the cues more than the screen. They're doing better on the search task, and they're using the automation more. So their trust increases in the undertrust. And on a scale of 0 to 100, we were able to increase, on average, by 17 points. Now, these are people. Some people who are undertrusting, we encouraged them, and their trust still went down. You know? Like I said, this is what we were able to do. But on average, we were able to show this amount of change. And the same thing with the extreme overtrust. We were able to decrease their effective trust based on their behaviors by 20 points. What? Oh, this is, these are box and whisker plots. So it's a mean, standard deviation, and extremes. Yes, this is the variance in their delta trust observed based on our model, right? So again, there's a lot of questions here. And here's one example output from the Kalman filter. So the purple line there is an example of a person going through the course, and you can see the encouraging messages they got. After the first encouraging message, their behavior didn't change too much, but after the second one, their trusting behaviors went up by quite a lot. And then when they were calibrated in those gray boxes, our estimate of their trust was appropriate for the course, so we didn't give them any warnings. And then after the course shifted, they were overtrusting it, and so we gave them a warning, and their trust behavior decreased. So this is just one example. We've got, I don't know how many plots like this, but they all kind of look the same. There's, some back and forth, and, each of these time slots is order of a minute observing their behavior. So, we try to make these studies that we can do within an hour, so people can come in between classes. It's like playing a video game. They get $15. If they do pretty well, they get more. It's what we're able to do within the limits. But this is, demonstrated that through these warnings, we were able to show that we could nudge their trust. I'm not sure this is total calibration, but we're starting to move them in the right direction. So that was the trust calibration piece. I'll spend a few minutes here talking about pedestrians, because we did some work with pedestrians too. Yes, Bill? Yes. That was what we said. The capabilities depend on the road, and we hope that their trust would also depend on the road conditions. Mm-hmm. So this is interesting because, as I mentioned, I spent some time walking around campus today, and absolutely pedestrians interact with cars all the time. So, and that is going to be a challenge for automated vehicles to interact with pedestrians. And so we wanted to think about how can we model those interactions and think about how an automated vehicle might react to a pedestrian who may cross and be wondering if the car is going to cross, etc. So we model these interactions as being fairly long duration, but we do assume that there's a structured environment, that there are sidewalks and crosswalks, and that pedestrians only cross at crosswalks. Now, I know that's a completely unreasonable assumption in a college town. It doesn't work in Ann Arbor either. But for these experiments, we assumed that they are, of course they are. That's what they're looking at. They're not looking at the cars. They're talking to their friends, or they're looking on their phones. Absolutely. They all have a phone. So we did some, I'll show you some of the experiments, but the interesting results were at what we call a mid-block crossing, where there's no stoplight or no stop sign and not even a cross street. It's just a crosswalk in the middle of the block. And we have a bunch of those around campus. I think you guys have some too. But that's where the right-of-way is a little unclear, right? It's a crosswalk. You're supposed to stop for the pedestrian in the crosswalk, but are they really going to cross? Hard to say. There have been a lot of, let's see. So here, urban scenarios, unsignalized mid-block crossing, sidewalks on both sides. Hard to say if the pedestrian's going to cross. So we want to be able to predict where the pedestrian is going to go, and then use that prediction to plan for the automated vehicle. Should it stop? Should it not stop? And try to make that comfortable both for the pedestrian as well as for the driver or passenger in the AV. And we're going to use a very simple model that there's 4 states for the pedestrian. They're approaching the crosswalk, they're waiting, they're crossing, and they're walking away. So we use these 4 hybrid states, or discrete event states, and a continuous variable model inside each discrete state, which is constant velocity. They're either walking at the constant velocity, or they're standing still, basically. Or they're turning, right? They've changed their direction. And we have these probabilities that we got from our experiments, and I'll show you what those data are. So between the probabilities of switching between these discrete states, a probability that they're going to approach the crosswalk and just walk away, probability that they start waiting, and then if they're waiting, their probability that they'll actually cross. If they cross, we basically assume they're going to continue walking away, but I think we flip a coin which direction they're going to go or something like that. But it doesn't really matter, because really what we're looking for is if they're approaching the crosswalk, how likely are they to cross, and when would they choose to cross? I should mention that there's been a lot of deep learning models, LSTM, you name it, that take tons of data from pedestrians and put them into these deep learning models and come up with projections of what pedestrians are going to do. They look at the angles of their arms and all kinds of things. And some of them have worked pretty well in a lot of cases, but it's hard to say how transferable they are. This model is pretty low budget computationally and pretty easy to set up. So I'll tell you how we get the data. We have what we call an omnidirectional treadmill, where we put people, again, mostly college students, into the VR headset. We strap them into this omnidirectional treadmill, and they walk in this urban environment. There's special shoes they have to wear that track their speed, and they can turn in any direction and then keep walking, and then the VR will follow them if they turn or go down the street. And so we make them walk across the street a number of times, pick up packages from one side, bring them to the other side, pick up packages and bring them back. And all the while, there's AVs, automated vehicles, driving up and down the road. And they have to decide when to cross. So again, we give them an incentive. They get more points if they get all the packages delivered rather quickly, but they lose points if the AVs get too close to them. They need to have some certain safe distance. You know, we don't let them walk right in front of the AVs and the AV stops. The AV will stop for them, but they'll lose points. So we want to try to find what that gap. So here we did 30 pedestrians, and you know they had to cross 540 times. And again, this is a mid-block. There's no stop sign, no stoplight, and they were incentivized to try to cross. So what we observed, and this is what we call the gap acceptance. So this is the probability distribution function, or the integral of it, of when they choose to cross, given the distance of the gap in seconds. How many seconds before the vehicle is expected to hit the crosswalk? And you can see if it's very short, they're not likely to cross. So the blue is from literature data, people crossing at crosswalks in the wild, and the black is from our experiments. So our pedestrians are a little more conservative. None of them start crossing until about 2.5 seconds, which is still pretty fast. But the shape of the curve is rather similar to what you see. And as long as the gap is supposed to be at least 5 seconds before the car gets there, they'll all start crossing, basically. So we use this probability distribution in our model. We also look at their speed. And their speed, of course, in the VR is how much their motions in the automated or the omnidirectional treadmill transfer to the environment that they're walking in. But you can see people walk faster when they're crossing than they do when they're on the sidewalk, in both cases. And the speeds are not significantly different. I mean, I could get you the standard deviations of this if you want, but we just showed that this is a reasonable approximation for people walking in VR versus in the wild. We did a few experiments at our test track M-City, but it was snowing that day, and the crosswalk was covered in snow, and so there were issues with that. And I think we only ran with about 5 subjects, and then it was Christmas. And anyways, interesting things. We saw similar results. Yeah. For getting too close. It could be.
The personal penalty for getting too close in the real world is probably less than what you said.
It's possible, and I think it also depends. If I was trying to cross on a college campus where I know the cars are really expecting me, I'm going to be a little more risky than if I'm in an unfamiliar environment and I don't know if the cars are really going to stop. So I think it's harder to say but that's an interesting hypothesis. So anyways, we built that hybrid systems model using this data that we have for pedestrian probability to cross, how fast do they walk, and then we looked at how are we going to use that prediction in a controller for an automated vehicle with 3 different objectives. We want to, of course, avoid the pedestrians. We want to get to where we're going quickly, so we want to get to our target while obeying the speed limit. And we want the passengers inside to be reasonably comfortable. So we put a cost penalty on acceleration and jerk. And we compare this with a baseline rule-based controller that basically drives the speed limit until they see someone in the crosswalk, and then they'll hard brake and stop, which usually has more acceleration, but it was just kind of the simplest rule-based controller that we compared to. Here's the unsignalized crosswalk. You can see the automated vehicle coming. And this is a 6.5-second gap, so this pedestrian is going to cross. The AV does have to slow down because they see the pedestrians crossing, and then they're able to, once they see the pedestrians far enough through the crosswalk, they can speed up and go, as long as there's not somebody else crossing. And so this is, the basic simulation results we have, where we compare, in thousands of simulations with, random pedestrians crossing. The baseline does hit very, lightly the pedestrians. They're going pretty slow by that time, and probably in real life, the pedestrian would have dropped, been able to either run or run out of the way. But the MPC controller that has this predictive model is able to, at least in simulation, guarantee that it never hits any pedestrians. So this is all in simulation. We had hoped to do studies in that omnidirectional treadmill with real people trying to walk across the automated vehicles with this controller, but then we had a pandemic. And so we haven't done any human studies for a couple of years, but this was a simulation study. Someone had a question. Well, it's the pedestrian is using that decision, and we pull random variables from that gap acceptance. When are they going to choose to cross? And again, from the distribution of walking speeds, we pull from those distributions to seed these simulations. Does that make sense? Okay. It's not deterministic. No, none of them are. They're all pulled from those distributions that I showed you. So again, just we were hopeful to be able to do these experiments with our treadmill, and then we had a pandemic, and the funding ran out, and the student graduated, and all those good things. So that's okay. We were able to do simulation studies. So I'll wrap up here with some conclusions, and happy to have some discussions about the future direction. So basically, what I told you today from our experiments, we believe you can estimate drivers' trust by watching what they're doing, their observed behaviors. And then we can calibrate that to some extent, nudge them to trust more or trust less. We can do some prediction of pedestrian behaviors. Modulo, we assume they cross at crosswalks, which is, a reasonable assumption in many cases, not totally true everywhere. And then we can use that prediction to allow the automated vehicles to react to that predicted behavior, while still trying to get to where they're going and not just be waiting to see if pedestrians will cross. I've been in that situation, I think, both as a driver and a pedestrian. Like, both of us are standing there. Are you going to go? Are you going to go? Who's going to go? So one of the things that we're really thinking about now is you could think of a driver in an automated vehicle as a team, right? There's a human and autonomy team, but we're really trying to think in more diverse domains, more humans, more vehicles, more automation. How can we use this idea of trust in human-robot teams in more diverse domains? And also, we keep talking about this, but we haven't really come up with some really good ways to think about how and when should the automation trust the human, right? If you have this automated driving system, now it does, can it do automated braking if the human's not paying attention to not run into something? Some cars have that, emergency braking. Certainly, we're all familiar by now with anti-lock brakes, which you could think of as a way to override the human's instinct to brake and pump the brakes when you're slipping on ice, and lane keeping. And so there are ideas of when automation should take over from the human, but that's also a slippery slope to go down. Shouldn't you always trust the human the most? And some cases, yes, and some cases, no. And when is that answer? Both ways, I think. Some ethical questions and some interesting things to think about. So that's the end of my formal presentation, and it was great to see some questions during the talk, and I'd be happy to take any more. Yes, Derek.
Thank you. Great talk. I love how you used the modeling and the data to try to describe some of these. So regarding the first part of the talk with trust, I think I followed the gist of the system identification. There are a few questions that have come up. One of which was just the configuration space for trust. So it's a scalar, but it seemed to me that the subjects in your study rated it from 0 to 100 perhaps. But the common filter wouldn't work on a nonlinear configuration space. So how did you model it? Was it a real number?
So the official trust study is like 15 or 20 questions that are rated on a Likert scale from 0 to 7. And so we rolled that into a 0 to 100. Put it on a 0 to 1. I mean, there's a lot of questions and there's a lot of, are they reliable? So that's how we did the original. And then when they report the change, did my trust increase by a lot or a little, decrease by a lot or a little? Those we just, again, scaled to make them constant increments. So there's not and the common filter, yeah, it doesn't deal with this nonlinearity, but we assumed it was linear around some nominal value that we didn't really talk too much about.
Yeah, because near the edges, the variance would go outside the bounds.
Absolutely.
Of that. And then, with a linear filter like that, it does depend on having a good initial estimate.
Yes.
Otherwise, you may never track the actual value.
So we initialize with the first, between when they start and when the first event is, we observe their values over that time interval and do the inverse of the matrix to find their original estimate.
Gotcha.
That's how we initialize, which is, again,
So then,
a reasonable assumption.
Yeah, absolutely. So then you were giving these verbal notifications based on this idea that if their trust was miscalibrated. But I missed how you determined what the correct level of trust should be.
Okay. So we had high, medium, low variables, and I'd have to go back and look at that plot, but I want to say high trust was above 75, and medium trust was between 25 and 75, and low was less than 25, or something like that. There were just lines we drew.
I see. So based on your estimate of the trust,
yeah.
then you cued on that. I see. So then the last variation, I run into this in my vehicle, because you're cueing the driver based on the estimate of the trust. If the estimate is incorrect, the cues might become undesirable.
Right.
Because maybe you estimate that the driver has a miscalibration of trust, but in fact the driver doesn't. So in effect, you might be reducing the trust just by
Because
virtue of the fact that
yes.
you're pinging them and annoying them.
Yep, that's a good. I don't think we got into that because we only had them for an hour and there were only 12 events, and so we probably didn't get to that. But you're right, that's a second order effect. Absolutely. Thank you for bringing that up.
Let's take more questions. Go ahead, please.
So I think it would be really interesting to look at what type of task you're asking the participant to do while they're trying to do the driving.
Absolutely.
Because you ask the focused type
It's
activity.
a visual search task, which is the same as
That's
driving.
one thing, but when the driver is sitting there, the participant, they can either mind wander, which would use certain part of the brain, which is different than when you are doing a focused task.
Right.
So if the person is switching between driving and mind wandering, would that change the level of trust they have in the autonomous vehicle, or and compare it to what happens if you're switching between the focused task and driving?
So there has been some work in that area because there's been a lot of work in the switching between the secondary task and the driving task, and people have looked at different, like this is a visual search task, right? They've also looked at audio tasks where you're supposed to listen to something and learn something. So they've been a lot of different things, and I'd say the results right now are inconclusive in terms of how these different types of tasks influence their ability to go back to the driving task and find their situation awareness again. But yeah, there are a lot of different things to be considered. That this is just a first estimate. Yes.
Okay. I guess this is piggybacking a little bit off of his question. Maybe this is a stupid question, but is there some ideal level of trust that, like, if a human felt that same curve, then they would be like the safest or like optimal safety while in traffic?
So I think that's why we didn't call it control, because it wasn't like we were trying to hit a set point. I think we wanted to keep the trust within a range. That, you know, between these two levels, it's not too much, it's not too little, it's the Goldilocks, you know, about the right amount. So I don't think there is an ideal level. I think there's kind of a range that would be reasonable, appropriate.
I guess I asked because you had a graph where it was like you get a warning based off of whether the trust is right or not. Like
Whether it's over or under, yeah. So
but it was like there was such a big dip in like suddenly not trusting the vehicle. So I was kind of wondering if you had some way of, like, I don't know.
Well, that big dip is probably because they had to take over the vehicle, so they weren't using the automation, and they're probably spending a lot more time looking at the road because they were worried.
Yeah.
So, anyways, Bill, you had a question.
Well, I always worry about experiments and what you need to control for.
Absolutely.
And so one aspect of this is that, as you can tell from my mask, there are situations where I'm not very trusting at all. And that's context dependent.
Mm-hmm.
So you need to, how do you account for the fact that not just me, most people would be much more trusting in an environment where the AI was likely to do better, as you know, and also where I'm more dependent on the accuracy of the trust.
Right.
I'm a lot more willing to risk a collision when I'm racing a sailboat than I am when I'm in a car.
Right. So we do, as part of the study, and I didn't report on it here, we do give them a lot of questionnaires about their propensity to trust, their experience in trust, and there are ways to correlate and correct some of these based on the individual preferences and experiences. But I will say, what we saw in our experiments is not a lot of difference, and partly probably because most of our subjects were undergraduate engineering students.
Yeah.
They have good experience with video games. You know, they're used to these kind of simulated environments, and they actually, students are much more likely to trust automation than people of different generations. Let's put it that way. So, so I think, yes, that's a limitation of our study, but it's also a sample of convenience, right?
Yeah.
They're easy to find. And they're willing to do it for $15 for an hour. Yes, John.
I have a question to ask you too.
Okay.
So the first one is, you know, when we work on these things, we try to put some tolerance on the trust. That's why I asked you the question for the variance, because we found that if you don't put tolerances, you get some of the phenomena that people observed before. I may be reacting too much, and so on and so forth.
Right.
Do you do that? Do you try to get some robustness into the trust, and robustness with respect to the parameters you use to evaluate the trust?
So we, not in this experiment. We just put kind of those thresholds in and thought that the scales were wide enough to be reasonable for the experiment that we ran.
We try to have a quantifiable measure of trust, and by that we mean something that can be calculated pretty fast based on variables that I have available to me.
Right.
Now, with respect to the second part of your talk, I visited your friend, Mariana Neto.
Ah, okay.
So they had a similar setup where they make you walk
Mm-hmm.
in a virtual environment. And what I wanted to ask is, when you calculate these probabilities of what the human's going to do with the pedestrian, they found that whether the traffic that they simulate in the VR is two directions or one direction, it affects the behavior of the human.
Absolutely.
Did you find the same?
We only did it with one directional traffic because we knew that was another variable to be controlled for.
It affects the probability, the model.
It's a 2-lane road, but they're all going the same direction.
And the other thing is, they also found that it's human impression. The size distribution of the vehicles, meaning if I have trucks or cars, also affects the behavior. In other words, you're going to be more hesitant to cross if a truck comes towards you with the same speed versus a car. Did you find similar?
I believe that we used all the same kind of vehicles. We tried to make it control as many variables as we could.
Yeah, but you know, that's in the what's called Eiffel satellite campus of the University of Paris. That's where I visited. And they put me through this corridor and the goggles, and I would see the cars coming by, and they were trying to get data from how I react. Yeah. Except I'm very risky. Okay, I take risks. So anyway, very nice talk. Thank you.
Thank you.
English?
Yes.
So, when you're trying to calibrate the trust and get the readings, like how do you set up the actual experiments? Like you're going to have a set of events that some are like safe, that's actually working as expected, and then some of them where, you know, the car is not doing what you expect and you have to look up. So when you're trying to do that, what if you clump up the ones that the car is not going to work in the beginning? Won't that create like lingering effects of, I'm never going to trust this car for the next 2 hours?
A lot of other people have done that, and so we tried to spread them out to not have that clustering effect. And we did not randomize when the trusting and the correct and incorrect ones. We did the same for everybody. Because again, there's lots of different variables that we didn't want to look at that effect. I mean, it is true. The more times the automation is wrong, the less they trust it. And if it's wrong often enough, then they just won't trust it at all. We made it right more than it was wrong.
You cannot use some of the automation to help you in the difficult roads, to ameliorate a little bit the dependence on trust. So, for instance, I can have controllers that they help drive the car differently when I have rough terrain.
We just tried to, tell the person that, the automation is better on straight roads, clear weather, and so.
You know what I mean?
Yes, I know. If the automation knows the road, it can drive.
But it can sense it.
Yeah.
Based on vibrations.
And it can drive slower. Yeah. Anyways, lots of different things you can do.
Yeah. Thank you.
Okay, you can see there are a lot of exciting questions, Don.
Yeah.
We can keep you for 2 more hours. But thank you, Don, again for wonderful talk.